So this lesson is looking at friction. I should give that a wavy underline really, looking at friction. So we talked in the first lesson about smooth and rough surfaces, and so whenever we have a rough surface we're going to have friction involved. As I'm sure you're aware, friction always acts to oppose motion. Now you don't actually have to have motion to have friction, but it would work in the direction that the object would be moving were there no friction. Now friction has a maximum value as we model it in M1, and that value, that maximum value, is called F max. So it's written like that and it's said F max. This is a product of a property between the surface and the object, which is known as coefficient of friction, which is mu. Coefficient of friction. And the other thing that affects friction is the normal reaction force. Now this is something you can easily think about. If you try and move a pen, push it across the table, it's really easy. If you push down hard on that pen, it becomes harder to move. Works especially well with your textbook. The reason for that is as you push down, you increase the normal reaction force. So, really important bit here is to learn this equation, which comes in for friction. And that equation is, write it in that box so that you remember to learn it. F max equals mu r, where mu is the coefficient of friction and r is the normal reaction force that we were talking about. When we're looking at an object that's moving, the friction that it experiences becomes that maximum value F max. That enables us to use our equation F max equals mu r when resolving our forces to link the two different directions together, which can be really useful at times. What this does often entail though is using simultaneous equations, because instead of just dealing with each direction independently, they're now linked. So let's get on with examples. We're going to start by looking horizontally. First example is this one. In these examples we're going to be looking at two things. First of all, is the object accelerating? This will be determined by looking at the maximum value of friction, and then from that, if it is accelerating, we want to find that acceleration. Now if we have something on a flat surface, we need to make sure we include the weight, which is mg, so in this case would be 5g. Don't forget that when we're looking in mechanics, g is 9.8. That is a perfectly accurate value. And we also need our normal reaction force so that we can find our coefficient of, so we can use our coefficient of friction to find our F max. Now, same as always, resolve in two different directions. So if I resolve vertically on this one, I'm going to get r minus 5g equals 0. Now I know this is equal to 0 because this object isn't floating, it's on that surface. So I know that r equals 5g, with g being 9.8, that's 49. I can now look at F max. So what I do is I say F max equals mu r, which equals 0.3 times 49. 0.3 times 49 is going to give us 14.7. Now, if f was 14.7, this object would be moving to the left. Now that clearly can't happen, because that means the friction would be pulling it in a certain direction. So the fact that F max is bigger than our force that's pulling us tells us that this object isn't accelerating, it just stays where it is. So there is no acceleration. So if you like, you can say A equals 0. And that's that first example done. Now if we look at this second example, we have similar situation. Now there's a couple of bits to point out on this. First of all, we need our 7G and our R. We also have this extra force which is pushing down on our object. Now we don't like forces that push. So if you ever get that in a situation, change that force to one pulling down. It's easier to see which way it's acting, because a pushing arrow looks like it's on the top, but it's actually acting downwards, and it's easy to get confused by that. Now I'm still going to start by resolving vertically. It always makes sense on these questions to resolve vertically to begin with, because we need to find R. So resolving up gives me R minus 7G minus 10 equals 0. So R equals 7G plus 10. So R equals 7G is 68.6 plus 10 gives us 78.6 newtons. Now what we look at now is F equals mu R. F max equals mu R, to find that maximum value of friction. So I'm just going to start here. F max equals mu R, which gives us mu is 0.4. 0.4 times 78.6. So that gives us a value of 31.44. Now you can clearly see that if that's F max, we have a much bigger force pulling, we are going to have an acceleration. So what we now have to do is resolve horizontally. This time we're going to be using Newton's second law, because there is an acceleration. So what that gives us is 90 minus F max equals 7a. Now a lot of people get confused because they've used 7g over here. They sometimes put a g in here. This is mass times acceleration. That one is a force, so it's a weight. So that's why one has a g and the other doesn't. So 90 minus F max equals 7a. We know F max, that gives us 90 minus 31.44 equals 7a. So 7a equals 58.56. So a equals, dividing by 7, 8.4 meters per second squared. So very similar principle to always, resolving in perpendicular directions. We've just worked out our F max in between. If you think you're happy with that, you can get on with those questions, which are on page 52 of the book. If not, watch the next video for the final example.